Hi, in this section we'll be looking at what is known as the squeeze theorem. This theorem, also known as the sandwich theorem, is often quite useful when trying to find the limits of seemingly very complicated functions. Let's suppose you have some function of f(x) and you're trying to find its limit as x approaches some a. Very often it's not going to be so easy and you end up with this type of indeterminate form when you try to simply substitute. However, if you can find two functions, some g of x and h of x, such that f of x is always between these, in other words, f of x is greater than or equal to h of x, and always less than or equal to g of x in some interval. Now, all these functions need to be defined over this interval, with the possible exception when x is equal to a. So if you have this situation here, then it will be true that the limit of f of x as x approaches a will be greater than or equal to the limit of h of x as x approaches a, and less than or equal to the limit of g of x as x approaches a. And so this is what we're going to make use of. If also we have that the limit of h of x as x approaches a is equal to the limit of g of x as x approaches a, and both being equal to some real number L, then obviously the limit of f of x as x approaches a is going to be greater than or equal to L and less than or equal to L. The only way this can be true is, of course, if the limit of f of x as x approaches a is equal to L. So what I have are two functions, g of x and h of x, that both converge to L as x approaches a. And I also know that f of x is always between these two. That means then that f of x has to be converging to L also. So this is very simple and almost like common sense. You probably look at this and say to yourself, why is this even a theorem? Well, most of us would not have thought of this before we saw it. So that's why it's very important, and we'll look at an example, a very famous classic example where this is applied. We're given this expression, the sine of some angle in radians divided by the angle, again in radians. This statement is saying that the limit of this expression as theta approaches 0 is going to be equal to 1. Now if you were to simply use substitution, this would not be clear at all. The sine of 0 is 0, and then this being 0, 0 divided by 0 is definitely not 1. You could apply an intuitive approach and look at this and say, well, this ratio here is simply the ratio of this line segment BC. Remember, this is the sine. So it's a ratio of this line segment to this arc being equal to the angle. Remember, in radians, the angle is expressed as the length of this segment divided by the radius, whose value for the unit circle is 1. What this is saying is that the ratio of the arc BD to the segment BC approaches 1 as this angle gets very, very small. And you can see that intuitively. However, let's also approach this problem using the theorem we just looked at. So let's just write out what we have here. The segment BC is going to be less than or equal to this arc BD. That should be very clear. And of course, this arc BD has to be less than or equal to the segment ED. Remember, we'll be making this angle smaller and smaller and bringing it very, very close to 0. This segment BC, as we have just stated, is the sine of the angle. The arc BD is the angle itself. And the segment ED is the tangent of the angle. So let's see that this is the tangent of the angle. The tangent of the angle is the opposite over the adjacent. The opposite is ED, and the adjacent is the radius of the circle, which is 1. Remember, we are using the unit circle. So now we have this compound inequality. We can divide throughout by the sine of the angle, which leaves us 1 theta over the sine of theta, and then this becomes 1 over the cosine of theta. Remember, tangent of the angle is sine over the cosine. So if you divide by the sine, you're left with 1 over the cosine of the angle. And then I take reciprocals across. That means we have to reverse these inequalities. So 1 now is going to be greater than or equal to sine of theta over theta, and this will be greater than the cosine of theta. We are now in a position to apply our squeeze theorem. We have this function here squeezed in or sandwiched in between these two. This will always be less than or equal to this. This will always be greater than or equal to this. We can take limits then as theta approaches 0 of the 1 of this expression and of this expression. Clearly the limit of 1 as theta approaches 0 is 1. The limit of this expression, well, that's what we want to find. And here we have the limit of the cosine of theta as theta approaches 0. Well, that's going to be 1. So if the limit as theta approaches 0 of the sine of theta divided by theta has to be less than or equal to 1 and greater than or equal to 1, then clearly the limit of the sine of theta divided by theta as theta approaches 0 has to be equal to 1. So this obviously has been a very easy thing to prove. Hence you see just how powerful the squeeze theorem can be. There are more difficult problems like this that can be solved using the squeeze theorem, and I recommend and urge that you look up in trigonometry textbooks for such problems and attempt them. We can look at this problem graphically. Because the software I use allows you to write functions of x only, I use x instead of theta. So here we have g of x equal 1. Here we have our f of x, which is sin of x over x. And here we have h of x equal cosine of x. And we're working in an interval where all the functions are defined with the possible exception of at this point. And we know that f of x is not going to be defined here, because we get an indeterminate form when we substitute 0 into this expression. We see both functions converge, both g of x and h of x converge to 1 as x approaches 0. That means f of x must also converge to 1. So this is very straightforward. There's nothing very complicated or complex about this idea. I urge you to try out more challenging problems, find a trigonometry textbook, and solve a few problems. So now let's look at a more formal definition of the squeeze theorem. Given three functions, f of x, g of x, and h of x, that are defined over an open interval containing x equal a, with a possible exception of when x is equal to a, then if f of x is greater than or equal to h of x and less than or equal to g of x in that interval, and the limit of these two functions as x approaches a is some real number L, then the limit of f of x as x approaches a is going to be L. So I hope you can look at something like this and read it and understand it. That's a very important skill. Okay, so bye for now.